Hello, welcome back. I think the other day I have given you a few cases of static friction. I discussed that, I think, in virtual great detail. When there is no relative motion, we take the friction there to be static friction. Okay? Now I go a bit ahead of it, and we would be virtually revisiting all those cases because my immediate purpose is minimum force required. Minimum force required to just move the body, obviously relative to the surface on which it is present. Okay? Right. Now, that is nothing but that F minimum, whatever you do, is nothing but FL. It should be. So every time I try to find out what is that limiting friction. Okay? Right. We will start right from the beginning as we discussed in the case of static frictional forces. Well, there is no complication here. This is, I am applying a force here and about to move, therefore FL, and so F is equal to FL is equal to mu Ln is equal to mu Lmg. What is the force exerted by the surface on the body or by the body on the surface? Total contact force. I already told you that this is how you have to do it, and this is nothing but this, and N is nothing but mg. So the magnitude will be mg into root of. I think I already gave it to you before. So this is the minimum force required for the body to slide on this surface. I hope this is clear. I'll go to the second case. Same, but this time I am pulling at an angle alpha. As before, mg n, that is f sin alpha, this is f cos alpha, about to move, therefore fl. About to move, therefore fl. So, what do you get? F cos alpha is fl, fl is mu Ln, and what is n here? N plus f sin alpha is equal to mg, or n is equal to. So you substitute it here, mu L into mg minus f sin alpha. Or you bring f sin alpha onto this side, so you get sin alpha. I am removing the subscript L, you can put it also. So F is equal to mu mg by cos alpha. This is what we call as pulling force. Previously you were in need of mu mg. Now it is mu mg by something. We will see what is this going to be. We'll make little jugglery here. You know that mu is equal to tan theta f or sin theta f by cos theta f. If you substitute it here, what do you get? mg sin theta f by cos theta f. Now here cos alpha plus sin theta f by cos theta f sin alpha. So take LCM, you get this cos theta f gets cancelled. So you get cos A cos B plus sin A sin B. So I can write this as cos A minus B. Cos alpha minus theta. This is the actual pulling force. Remember, this cos function is always less than 1. Therefore, you are dividing this with a certain value, and supposing I am now looking at the minimum pulling force. You are equated to FL, that is fine. But there is a function here. So minimum means this must be maximum. When is this maximum? When cos of all this is equal to 1, or this parenthesis must be equal to 0, so that alpha equal to theta f, and that leads to what? F minimum pulling. Alpha theta f means this becomes 1. This is mg sin theta f. But if you recall, sin theta f is now you can compare your horizontal. First case, mu mg. Now in denominator is something more than 1. Therefore, the minimum pulling force is so much, is less than even that horizontal force. Now this is the least ever force to just move the body. When is this possible? Well, alpha is equal to theta f. You understand this? What is theta f? Theta f is tan inverse mu. Because tan theta f is equal to mu. So, what is the least ever force means what will you give? You have to pull the body at an angle equal to angle of friction, or tan inverse mu. Then the magnitude of such minimum force is mu mg by root of 1 plus mu square. I hope this is clear. This is a very important point. Is this okay now? Right. Now what I do, instead of pulling, I want to push it. So I'll just do right opposite to this. If I do that, you know what will happen? F sin alpha downwards, therefore this becomes minus once the force is like this. This will be plus, and here it will be plus. This is the case of pushing. You get some peculiar case in the case of pushing. Now alpha plus theta. So what is that pushing force? Pushing force is mg sin theta f by. So minimum pushing doesn't have it because this becomes a negative. Alpha plus theta f is equal to 0. Alpha is equal to minus theta. So that is the amounts to pulling. But what is important here is you look at the value. Once you do that, you know that this is a very high value compared to any of the two previous cases. I'll tell you why. I take a case where, special case, suppose if alpha plus theta f is equal to, I'm not doing all that analysis. This is F sin alpha, F cos alpha, this is FL, N, and G. This is the correct figure. And once you put that, I'm saying this alpha, it must be plus theta is equal to pi by 2, or alpha is complementary angle to angle of friction. Complementary to angle of friction. Then what happens? This becomes 0, this becomes infinity. Very important case. What do you mean by F pushing infinity? That means no matter what force you apply, it is impossible to move the body through pushing. If you take at an angle, alpha is greater than or equal to theta.